All right. So last week we started talking about dynamic programming, or more particularly, how to compute shortest path. And we looked at uses of shortest path in computer vision. So this is what we've been talking about last time. And today we will be here. We will talk about a slight generalization of the shortest path problem, allowing us to work on tree-shaped graphs. And so that is, the shortest path problem is a strict subproblem of what we will talk about today. And this, we already saw that shortest path give you a lot of modeling power in computer vision. But what we will see today, well, being slightly more general, gives you even more modeling power. And I want to show you a few examples of where this can be used. So why would you be interested? For example, to help you model connectivity. I have here a figure from a paper by the Daniel Kremer's lab from, I think, 2013. They were studying lung tissue at the time. And if you try and do semantic segmentation, you will obtain, of the airways in this case, you will obtain an image like so. You see the airways, they're heavily fractured just because the data is not so great. So this was 2013. If you use CNN, you will do slightly better, but still you will get these disconnected fragments. But here we do have prior knowledge, namely that fundamentally these airways in each lung, they form a tree. And if you do exploit this prior knowledge, this tree prior, then using the same kind of features, you would get a much more consistent image. And on the left is when you apply that to a whole lung. And I'll show you more pictures later. So this is one possible use case. Another possible use case is to model hierarchies. So sometimes it is not quite clear what is the best segmentation. So take this microscopy image here. We see these blobs, and one possibility is to, well, use a threshold that you make more and more stringent. For a very loose threshold, we get this green segment here, which in this case compasses many cells. If you use a stricter threshold, we get these groups of what I think are 2 red cells, 2 blue cells, and 1 yellow cell, and so on. The problem is there is probably no single threshold which really works perfectly across the image. So I would say that maybe in this one here, we get the number of cells right, but they become too small. So if you look at the yellow cell here, it really covers only a small part of what it should be covering. So what we want is something more like an adaptive threshold. So probably I would want to segment the red cells like so. The blue cells, actually, I think that these are, yeah, we want 2 cells. So the blue cells like so, but the yellow cell maybe like so. So you see that this threshold here has not been uniform, but I've made it somehow locally adaptive. And of course, I want to make that locally adaptive based on cues. And because these regions are nested, because they form hierarchy, because they are a tree, I can use dynamic programming on tree to find an optimal threshold here. So beautiful work by Carlos Ortita, Victor Lempitsky, and Andrew Scissorman. And the final example I want to give, also here borrowing slides from Andrew Scissorman, who is one of the all-stars of computer vision, really amazing scientist. The example given here is one of finding facial features. So you can, obviously this is a tree, at least in the graph sense. What is a tree in the graph sense? Well, a graph, as you know, is a collection of nodes connected by vertices. And if the graph has no loops, then you call it a tree. And because here we have these nodes, so eye, nose, mouth, and the vertices, and because in this particular graph there are no loops, this is why this is a tree, and this is why one can efficiently optimize energy functions such as this one, where for each possible eye position and mouth position and so on, we get a score. But we also want to take into account the relative placement of these hits. So in particular, what's often used is here a harmonic potential, so a spring with an equilibrium length of the expected nose tip to eye distance. And this is here a pairwise potential. And then the overall problem here, well, is an energy function defined over a tree, which can be optimized efficiently. And for example, well, for most faces, this would be an implausible configuration, or in particular, if the nose were found above the eyes, this would be even more improbable. And this is why this kind of model can help. It also has its limitations, because I was mentioning that it only understands, it only models what's shown here by the red lines. So in particular, if the eyes are above or below the nose is not something which the model is going to be able to discriminate. The only thing that it can understand is the distances are about right. Yeah? So to talk about the limitations here, so if we had the nose, and then if we found, all right, if we just talk about distances, then it would not even be able to figure out or complain if the left and the right eye are found in the same position. However, it is also possible in these pairwise potentials to use an equilibrium position. So for example, we can say that relative, if we use the nose as the anchor, it's very plausible, right? If we use the nose as an anchor, then we can say there is an expected equilibrium position of where the eye should be, and this is defined relative to the nose, like so many pixels to the right and so many pixels to the top. And then for deviations from this expected position, we would then have our, for example, quadratic potential that penalizes displacements of the eye relative to the expected position. But still, in terms of a graph, this would be a tree, and this is why we talk about it in today's context. All right. Now, before we talk about trees, a short recap, and I also want to introduce again this kind of picture here, a factor graph. So let's recall, what is the shortest path problem about? Shortest path, find as a globally optimal solution to the following optimization problem. If I have a couple of variables z, here I pretend that z is a indicator variable which indicates which state is active. So I could also, so I have a total of n of these variables. I could also have said that I'm minimizing over these n variables. To be super explicit, I could say, zi from I equals 1 to n. And each of these zi's is a vector, right? So in this example here, for example, each vector can have 5 possible states, and altogether this would be a variable z1. Then these here altogether, this would be my vector z2, z3, and so on. All right, and we now have a cost associated. With the different states of each individual random variable. In this picture by Prince, these costs were shown in this upper right corner. Yeah? So 5.7 or 1.0, 2.4, this was the unary cost associated with variable z3 taking on its state 1 or 2 or 3. Yeah? So these would be the unary costs, and in the last time we saw, for example, in this matching problem of stereo images, how these unary costs arise. Yeah, so how they are informed by the image data. Well, and secondly, we have here a pairwise potential or a pairwise cost. And well, let's look at those pairwise costs. Here they're written in besides these arrows. And we see a pattern here. So first of all, from any given variable, we only allow transitions to the same state or to the adjacent state. We do not allow, we simply disallow even bigger transitions. So this one here is taboo, and this one is taboo. It has a cost of infinity, or it simply doesn't have an edge in this graph. And then the other bit of pattern that we see is that if we don't change the state, we incur a cost of 0. There's no penalty. But if we do change the state by 1 unit, then we pay a cost of 2. All right, and these here are these pairwise potentials. In the particular case here, these incorporate a prior assumption regarding the smoothness of the data, and they are not informed by the local image content. It's always 0 or a cost of 2 or a cost of 2, regardless of what the image looks like locally. You could change that. You could say that, well, if in the image I see real boundary evidence, then I don't penalize a change of states, for example. Yes, you have lots of modeling power here, and if you do something like that, it does increase the expressivity of your model. All right, but anyway, we have this optimization problem, and I've argued last time that the unary costs can always be absorbed in the pairwise costs, and this is why down here I've only written the pairwise costs and I put the tilde on these pairwise potentials to indicate that they have absorbed the unaries. All right, so this is the optimization problem, and in terms of a factor graph, this is how I would draw it. A circle for each variable that I want to optimize, and you see these tiny black boxes here, and these represent the factors. Yeah, so for example, this here, this black box would represent the factor 2, 3, which relates, or which gives us the penalty if I'm in such and such state in variable 2 and in such and such state in variable number 3. Good, and then you saw, by the way, in Viterbi's algorithm, if we use a source here, we connect the source with costs of 0 to all the start edges. If we put a sink or a terminal T here, again with costs of 0, then in this directed acyclic graph from left to right, in this case we can use the Viterbi algorithm to always find the cheapest way of reaching a particular variable. So this particular state, the cheapest way, the overall cheapest way of reaching it would be from here. And now we see in these boxes the cumulative cost. So the cheapest way of reaching this particular node here by any path was 9.6, and the last bit of the path was that one. And by backtracking, I can recursively, reconstruct the entire cheapest or shortest path to this particular node. But here we're interested in the overall shortest path. So we look in the last row, where do we find the lowest accumulated cost? The lowest accumulated cost was here, 17.4. And then we trace back to find the shortest path, and that was shown here in red. All right, again, as a vector graph, this is what it looks like. Why do we talk about it so much? Because if we have n variables with capital K states each, the naive strategy would be exponential in cost, and by using the fact that our problem can be solved sequentially if done right, this only costs here of the order of number of variables times number of states squared. Good, this was a recap from last time. And we now will move on and generalize this to trees. Not just open chains as we have seen now.